So, any questions about the final exam or about the content so far of this course? If so, please let me know. Well, sample open question is difficult because it's always difficult for me to find such questions. I can, but I can give you the open questions of last term's exam. Just a moment. At least one of them. Yes, the exams will be different. So I've just copied the first open question of last year's exam, so that you get an impression. We have not yet talked about that, so I will present this later, this content of the course. So the question was, imagine to have 2018 data of area covered by bamboo forest in square kilometers. This should be square kilometers for each province in southern China. You should design two choropleth maps based on two different standardization methods. For both maps, the quantized method for classification would be used. Your task in this exam is not to design the two maps, but to describe two standardization methods to adjust these area-based raw totals to account for varying sizes of provinces. Which data would you need? How would you compute the standardized values? Describe also the consequences. What would be the difference between the two resulting maps? Which comparisons between provinces are possible? Which questions could be answered by analyzing these maps? Which standardization method would you prefer and why? So, of course, you have to know about the standardization methods. You have to know what the quantile method means for classification so that you can really understand the whole question and what you should do now. So I think it's From my point of view, it's not difficult, but I understand that it's a bit difficult to understand the question. So if you have not really understood what's going on in these parts of the materials, then it will be difficult for you to answer this question. So I hope this helps a bit. It's important, of course, that you see it's not too easy. You have to, you have to learn these materials. You have to understand what's going on. You have to know about the technical terms. Otherwise, it will be difficult. So after we have discussed these classification methods, we have discussed standardization, and we have discussed choropleth maps, then read this text again. So maybe copy it, save it, and keep it. And after we have discussed these topics, read this question again. Then I'm sure it's not that difficult at the moment, I guess. It's quite strange for you and hard to understand what's going on. But that's just natural because you're not familiar with the content so far. Okay, then I want to continue. The next section is about the perceptual consequences for information visualization. The main source here is the very good book by Colin Ware. I've uploaded that one for you. So you have also the original source of most of the examples and most of the text that is used here in this section. The first topic here is pre-attentive processing. Pre here means before. So before attention takes place. Pre-attentive processing is central to how we understand visual distinctiveness. Because visual distinctiveness is, of course, different depending on which kind of variables. So how we manipulate the different parts within a visual scene or image. Despite these processes are not fully independent from attention, so they do not occur entirely before attention comes into play, although this prefix pre suggests that they are less influenced by top-down processes. So pre-attentive, again, it means before attention, directly translated, but as you see here, it's not fully, these processes are not fully independent from attention. And attention is something that is a top-down process. So if we attend to something, then we are interested in that. So we want to see a certain part of an image, or we move our head or eyes in a certain direction. This is in part controlled by our mind, and therefore it's top down. But these pre-attentive processes, they are less influenced by these top-down processes. So in part, they are independent from that. That also means we cannot influence it fully. Part of this is not influenceable by us. A typical experiment conducted to find out whether some pattern is pre-attentively distinct involves measuring the response time to find the target among a set of other symbols called distractors. For example, finding threes in a set of other numbers. So to find all numbers 3 in a set of other numbers. So there are attractors and distractors. If you should find the number 3 or all the numbers 3 in a set of other numbers, then this number 3 is the attractor and all the other numbers are the distractors. So you see that here in the example, you have many numbers here. Some of these numbers are 3. But in the first way to present these numbers, A, all the numbers are black. They are same size, same thickness, same color. So there is no difference. The only difference is the shape. To count all the 3s now here in this table of digits, it is necessary to scan the numbers sequentially. That means one by one after another. So you have to start here and then you check, where is the 3? Where is the 3? Here. Here's the first 3. So this, of course, needs a lot of time. It's totally different in B. Here, to count the 3s in this table, it is only necessary to scan the red 3s because they pop out from their surroundings. This is because color is pre-attentively processed. Color is pre-attentively processed. So you look at these numbers here and you immediately see all the number 3s. They pop out. You look at that, you just need to count them, and then you see immediately, okay, 1, 2, 3, 4, 5, 6. There are 6 3s. This is much faster, and therefore it's important to use such variables. This is important for our visualization task. Now, if processing is pre-attentive, the time taken to find the target should be equally fast, no matter how many distracting non-targets there are. As an approximation, anything that is processed at a rate faster than 10 milliseconds per item is considered to be pre-attentive. Typical processing rates for non-pre-attentive targets are 40 milliseconds per item and more. So this is just a rule of thumb, just a rough approximation. So 10 milliseconds or lower is usually pre-attentive. If it's longer, 40 or more, 40 milliseconds or longer, then it's not pre-attentive. And you see this idea in the first paragraph of the last slide. So typical results from a pattern of pre-attentive processing. You can see here the gray circles show time to perceive an object that is pre-attentively distinct from its surroundings. In this case, time to process is independent of the number of distractors. The red X's show how time to process non-preattentively distinct targets increase with the number of distractors. So if it's preattentive, here you have the number of distractors is rising, but the response time is always the same. This is the theory about preattentive processing. If it's not preattentive, if you have more distractors, you need more time. Just think about the numbers before here in this example. So this first part is not preattentive. If you have more numbers here, you need more time. But here, for example, if you have twice as much numbers, you can still see immediately how many threes are there. So the number will not increase, or only minimal. That's the difference. Of course, here in theory, they say the time is exactly the same, but maybe, of course, you need a little bit more time, but it's still more or less the same. Totally different with not preattentive processing. There the time increases largely, so that it's much longer than if you have more items, more distractors. Preattentive processing is very important because if you want someone to instantaneously, so immediately, identify some marks on a map as being of type A, it should be differentiated from all other marks in a preattentive way. Of course, because this speeds up the whole process of reading the map. Not all preattentive effects are equally strong. There are degrees of preattentiveness. The strongest effects are based on color, orientation, size, contrast, and motion or blinking. But there are also degrees of differences within these variables. For example, large color differences work better than small ones. So if you have a high contrast, for example, this is better. So if the threes in the list above are just gray and all other numbers are black, it would be harder. But if you use red, this pops out more, and you see there's a degree of this preattentiveness. Here are examples for preattentively processed features. So, orientation. If you look at those vertical lines, there is one that is more diagonal, and it pops out. So you look at this, and you immediately see that one is different. This one is, it's different than the others. It pops out. The same is true here. The same is true here. Here it's more difficult. Also, size also plays a role here. As you see here, size pops out well. But here, although it's not just shape, or it's from my point of view, it's more size than shape, because length is also, it's also size related, of course. But this doesn't work well here. And you see there are degrees. Also color, when you look at that, it pops out. But of course, if you are color blind, if you have problems with certain colors, this will maybe not work, but this will still work. So this is also independent from color blindness. Also, this is another topic, color blindness. But you see there are degrees. This one is definitely the weakest of all these 6 examples. And here we have pre-attentively as well as not pre-attentively processed features. So light, dark, this is related to color. Enclosure, so enclosure or not enclosure. Convex or concave, so this has to do with depth cues. Addition, so these three or these four, these three and that one, so these four together, they are all pre-attentively processed. These two are not. So here I would say it's weak. There's a weak effect, but it's too weak. So it's not pre-attentively processed. And parallelism also not. So only these two are parallel lines, but they do not pop out because the difference is too small, the difference in angles. And you have to check them, yes, one by one to check if the lines are parallel or not. So this is not pre-attentively processed. Among the features that are pre-attentively processed are the following: line orientation, line length, line width, size, curvature, spatial grouping, blur or depth of field, added marks, numerosity. So this is how many? It's about number. So numerosity, 1, 2, 3 objects. Color, hue intensity, and motion flicker. Direction of motion, 2D spatial position. Also stereoscopic depth and convex concave shape from shading. So you see there are also depth cues involved here. They can help to help that one item stands out compared to others. Here is such an example with depth cues. This is a shape from shading, and this is this one works pre-attentively, so you immediately see the two different groups of items. But here on the right-hand side, if you have just a binary version, binary here means it's just black and white, so just 0 and 1 binary, black and white versions. Here, this one is not pre-attentively processed. So this one is not. And the reason is that this here is also a depth cue. So we see the bit three-dimensional. This has to do with the interesting fact that if we have a shading that emulates like a light source from top left corner of the display. So if somewhere here is a light source shining, or the light comes from here, like the sun shining in this direction, so the shadow is here or here on that side, then these circles, they look like small hills, while these here look like small or shallow pits. This has to do with this shading experience. As you know, shading is used on maps also to give a better impression of the mountains and valleys and so on. And this is a strong variable to give you this impression and to use this pre-attentive processing. The question of which visual dimensions are pre-attentively stronger and therefore more salient cannot be answered in a simple way, because it always depends on the strength of the particular feature and the context. So it's difficult to to define certain rules. What is salience? So more salient, this term here. Salience of an item means the state or quality by which it stands out relative to its neighbors. So, and if it clearly stands out, then it's usually pre-attentive. But it's a degree, as you have seen, so it's not a question of yes, it stands out, or no, it stands not out. There are many degrees in between, so it stands a little bit out or a little bit more, and therefore it's often difficult to clearly say if it's really pre-attentive or not. Two factors are important in determining whether something stands out pre-attentively or not. First, the degree of difference of the target from non-targets. So is the degree high if the target is red and the non-targets are black, for example. And second, the degree of difference of non-targets from each other. So all the non-targets, the distractors, how different are they? Are they very different or very similar? So here you see that, for example. So the distractor, D is distractor and T is target. The distractor is a vertical line, while the right slanted line is the target. Here it's easy. You immediately see the target. So this is pre-attentively processed. But if you have many different kinds of distractors, they're all different, of course, to the target, otherwise it would not work. But now you have so many angles involved that it's much more difficult to find the target. So this is not pre-attentively processed here. There are asymmetries in some pre-attentive factors. What does it mean? This means, for example, adding marks to highlight a symbol is generally better than taking them away. If all of the symbols in a set except for a target object have an added mark, the target will be less distinctive. But if just one object has an added mark, it will be more distinctive. This is meant here with asymmetry or asymmetry. Another asymmetry is that a big target is easier to see surrounded by small targets than a small target surrounded by big targets, because we usually look first at the big target, even if there are many big targets. And then it depends also on the configuration. So where are the targets and the distractors? For highlighting, use whatever feature dimension is used least in other parts of the design. So for example, in this example here, all these distractors, the difference is just in the angle. And the target also has a different angle. So it's still all these different lines differentiated by their angle. Therefore, it is not a good idea to have just the target visualized with another angle. So not the same, but a different variable, for example, color or size. If it would be larger, thicker, for example, a thicker line, then it would pop out. If it's a red line, then it would pop out. But if there are so many lines with different angles and the target is just another different angle, then it will not pop out. So this is meant here by this last sentence. use whatever feature dimension is used least in other parts of the design. Using motion or blink highlighting can be very effective. So sometimes, for example, if we, in the World Wide Web, if we check out some sites there and you read a text and all of a sudden there is some blinking symbol, it always attracts us. So our attention moves to this object. We have to take a look what's going on there. So blinking or moving objects are very effective to draw our attention to these objects. So here you have now an example for highlighting methods that use positive asymmetric pre-attentive cues. Sharpness, so this is another name for depth of field. It's also one of the examples. You remember the chessboard with some figures that are sharp and others are blurred. So this is also a depth cue. So these sharp ones, they look nearer to us usually, and the blurred ones look like they are more far away. It could also be the other way around, but at least you see them in different levels usually. And this is a relatively strong pre-attentive effect. And added a surrounding feature here, or adding some shape or some object. This stands out then. So this is it's asymmetric, because if you would do it the other way around, so if all these circles are within a rectangle and just the target is not, then this would be harder. Therefore, it's asymmetric. And here's the same. If you would add such shape to all the circles except the target, so only the target has no such shape added, then it would be more difficult. Therefore, here we have this asymmetric pre-attentive cues. To make symbols in a set maximally distinctive, use redundant coding. For example, make symbols differ in both shape and color. Redundant coding, that means you code the information not just with one variable, but with two. So if you think about the first example with the red 3 popping out in all these other numbers, they're all black. The difference was just color, but you could add, for example, size. If the number 3 is not just only red, but also larger, then the effect would even be stronger. So this is redundant coding. And redundant coding allows for parallel search for each attribute used in the coding process, which gives you another option, an additional option. The situation is totally different if we have to search for targets with two feature attributes among distractors that share one or the other feature attribute. This sounds a bit difficult and confusing, but you will see that in the examples. For example, searching for a red square among red circles, black squares, and black circles. So you see there are some features they have in common, and therefore it's much more difficult. This slows down the searching process. In such a conjunction search, so this is called a conjunction search, we are forced to do a serial search which is slow and not pre-attentive, with few exceptions. So serial or sequential is like with all the black numbers, and we search for the 3s in these numbers. We have to check the whole series of numbers and search for the 3s. This is sequential or serial, one after another. This is slow. And here you have some examples. So this is about birds, different kinds of birds, and their beaks. So beaks have here different characterizations. So beak is the name for, let's say, the mouth of a bird, called beak, and its width and its length. And here you have the different types of birds, so different kinds of birds. And then you have here each symbol is for one individual bird. And these are the groups to the types they belong to. And now you have three different ways how to visualize this. Visual feature channels, similar to visual dimensions or visual variables, can be used to make symbols more distinct from one another. Center and right are examples for redundant coding. Center and right. So here we have only variation in shape, and this is much more difficult. So we need more time. We have to check the shapes, because there are three shapes, and therefore it's more difficult. It's still possible, of course, but it's more time intensive. Here we have shape and color, which makes it much easier. So here we look at this and immediately we see the groups, which is much harder here on the left-hand side. And on the right-hand side, we have variation in shape, color, and sharpness. So even three variables. And the effect is even stronger. So here it's easier to separate the three groups, the three types of birds, than here, and here it's better than here. So you see the different variations. You see how the different ways to visualize this data makes it easier or more difficult for the users. Of course, sometimes we have just a black and white publication, and it's not possible to publish it. We could use them size, of course, but this has the disadvantage that if some of these symbols are larger, then it looks like these birds are more important or something like that. So it's difficult then to treat all the birds equally. So we don't want one group to stand out looking like it is more important than the other groups. We want that the three groups look about equally important. But you can say, and this is right, it's also not really true here, because if you use blur effect, so the depth of field, then usually the sharp objects look like being more important and so on. So you have a bit this problem here. This is a very nice example. Here you see the problems that you get in these conjunction searches or conjunction tasks. Searching for the red squares is slow here because they are identified by a conjunction of shape and color. So you're looking for red squares. You're not just looking for red objects. You're not looking for just squares, but for red squares. And there are distractors that are red, but not squares, and there are distractors that are squares, but not red. Therefore, you have to check one by one. So you can separate easily red from black, but then you have to check where is the different shape within the red ones. This slows the whole process down. New pre-attentive dimension pairs allow for conjunctive search. Examples are luminance, polarity, and shape. Luminance polarity means that there are objects lighter and darker than a gray background. stereoscopic depth and color or movement, convexity, concavity, and color, with shape from shading as depth Q, or motion and shape or color. So with these combinations of variables, conjunction search works well, so pre-attentive. And here you see an example. The white circles are a conjunction of shape and luminance polarity. Nevertheless, they can be found pre-attentively. So if you search for the white circles here, you can see them immediately. This is quite interesting. So compared to the example before here, but of course, in the gray example, the sizes are also a bit different. But still, it works better than here. So here it takes longer to find all the circles. There are also many more circles. Here's about the red squares, sorry. Here's about the red squares. And there are 3, I think. 3 red squares. And to find them, you need more time than to find the 3 white circles here. Therefore, this works better than the other one. But in the other examples, squares are used, while here are these rectangles, which are also smaller. So this distance here is smaller than here. I think this has also an additional effect. So therefore, we could say that size plays a bit of role here. But again, still this one works better, which is also it's additionally fascinating because usually we always think if we use colorful symbols, we use an additional color, that this would increase the distinctiveness of symbols and makes it easier to do such a search. But in this case, that's not true. The gray, with different gray tones, work better than the colorful version. The next aspect here is about integral and separable dimensions. First, integral dimensions. So 2 or more attributes of a visual object are perceived holistically and not independently. Holistically means as a whole. Independently means separately from each other. For example, the combination of green light and red light is seen holistically as yellow light, so like a mixture. And it is difficult to respond independently to the red and green components because we see it as just one light tone. The situation is totally different with separable dimensions. People tend to make separate judgments about each graphical dimension, also called analytical processing. For example, the combination of color and size can be processed relatively independently. So it is easy to attend to one dimension or the other. So you can check the color or you can check the size of an object. You can deal with these 2 different variables in a different way. So you can separate them. So therefore they are separable, or these are separable dimensions. Yes, before I explain it with an example, let's have the second break now. Integral dimensions and separable dimensions. This is the topic right now. And it's easier to understand these two concepts. This is the example here. So the A here, this are the two different versions. So in the first one here, the width and height of an ellipse are perceived integrally, so the ellipses are seen as more similar to each other. Here, the width here of these two are the same. but this is a circle and these two are ellipses. And for us, these two look more similar because they have the same shape. The color and height of a shape are perceived separately, so the two green shapes are seen as most similar here. Now we think these two are more similar. And this B and C are just space plots of the two examples. So here you have height. This is the same in the two examples, and the width. But here color is the difference. So color 1, color 2, green and orange. And here you have more items. You have sets of patterns for a speeded classification task. So speeded means it's about time. So time is measured in an experiment. You have to classify the different objects, the items, and the time, how much time you need, this is measured, and compare them, of course. So which works faster? In both cases, A and B participants are laser pointer are required to respond positively to only those symbols that have the same height as the bar in the upper left corner. So this bar here, the upper left corner, this height, this is the relevant variable. The interference condition is on the left in both A and B. So in here we have this interference of different variables, the left side. A left here, the variable width interferes with classification based on height. B left here, the variable color does not interfere with classification based on height. A right here, right side, redundant size coding speeds classification. And B on the right hand side, redundant color and size coding does not speed classification. It's quite obvious here that if you just have to check the height of these different items, the color doesn't make a difference, not much. Of course, when you have found out that this and the yellow one is the same, then it's even faster, because then it's redundant. But here you have your how to say, it's no, it's not. Yeah, it's a bit. It confuses the search for the right height if you have the different width of the objects. And so here is no confusion about that. You can just concentrate on the diameter of these circles, and because the diameter is the same as the height here, and therefore this is faster then. And therefore the redundant coding here speeds up classification. Yes, a short excursus. That means a bit different topic, but it's related to this example here about color vision deficiencies. I mentioned the color blindness before, and this is important to know. If we talk about visualization, we need to know about that, because there are different kinds of color vision deficiencies. And The most important number you have here, roughly 8% of men and just 0.5% of women are affected of the red-green problem. So the mixture of red and green. Here you see an example. So if someone has this kind of color deficiency, red and green looks nearly the same, these two. This is the problem. So here the apples also, they look very similar then. Or here you have the impression of a real world scene of a rose. So red-green color blindness is the most common color vision deficiency. 4 different deficiencies make up the common wording red-green color blindness. People suffering from an anomaly are trichromats, but do report problems in color perception in the green, yellow, red sector of the spectrum. So anomaly is here. These two are anomalies. And these people are trichromats. That means they can differentiate between 3 colors. 3. Chroma is about color. 3 is about 3. The 2 different anomaly types show a less sensitiveness either to red light, this is proton, so they have a lower sensitiveness to red light, or to green light, this is deuton. You don't need to know these different kinds here, but you need to know this number here. You need to know that 8% of men have a kind of red-green color blindness. This is a very important number. And people suffering from an anopia are dichromats. So there are trichromats and dichromats. D now is only 2 colors. So they have a problem with one of the colors. They cannot see certain wavelengths in the spectrum. So they are completely lacking one type of retinal cones, therefore. You remember there are these different kinds of cones, 3 different types. They're sensitive to different parts of the wavelength of the spectrum, red, green, and blue. And so if one of these cones is absent, is not there, is missing, then you can, of course, not see this kind of color. So this is the bigger problem. And you see the numbers are, together the numbers are lower. So the largest group are the deuton anomaly males. This is the largest group. But altogether, if you sum up these numbers here, it's about 8% of men who have a problem with red-green differentiation. So maybe also some of you, as 8%, I have not counted the number of males in our group here of the students, but if there are about, let's say 40, then 4 would be 10%. So maybe about 2 or 3 of the male students in our class, in our course, have this problem, statistically seen. Therefore, it's something we have to think about when we produce visualizations. And here is a test, the Ishihara test, so developed from a Japanese scholar called Ishihara. It's a test for color blindness, so everyone can try that. And this is what people with regular vision see. And this is what the red-green colorblind people see. So they have difficulty to see the numbers here, and here, and also here. So if for you there is not really a difference between the 2 sides, then you have problem with this color deficiencies, color vision deficiencies. Therefore, in some cases, using redundant separable codes may still be desirable. For example, if both color and shape are used for information coding, individuals with color vision deficiencies will still have access to the information, like here. So it's not just the difference in color. So if the person is colorblind, these two would look very similar. But of course, there is still a distinction in the shape. Therefore, you have a redundancy. The same information is coded by color. Red is hospital, green is pharmacy. And it's also encoded by the shape. So you have a rectangle for hospital and a circle for pharmacy. So 2 times the same information, but different variables. This means it's redundant coded. Now back to integral and separable dimensions. Symbols, usually relatively small ones that represent quantity, are called glyphs. If it is important for people to respond holistically to a combination of 2 variables in a set of glyphs, variables should be mapped to integral glyph properties. If it is important for people to respond analytically to a combination of 2 or more variables, making separate judgments on the basis of one variable or the other, variables should be mapped to separable glyph properties. This one is an interesting example for a visualization with data glyphs. So a glyph here is these small objects that you can separate here from each other. So they have different size, different shape, different color, different orientation. And they are designed to represent many variables. 3 variables are mapped to the color of the lozenge-like glyphs. So lozenge is a general term for usually in medicine. If you take some medicines, some tablets, then this is one kind of shape that you can get. Although the shape is varying here a bit, but it looks a bit like a medicine that you can swallow, and therefore this term is used here. And so some 3 variables are mapped to the color of these glyphs, and some variables are mapped to their shape and orientation. The color mapped variables tend to be seen integrally and independently, separately from the shape orientation variables. So you can check the different color areas here. Although it's more or less continuous tone, so you have many, many colors here, not just a few classes. And so you can, these color variables tend to be seen integrally and independently from shape orientation variables. They also tend to be viewed holistically. Also, several depth cues are applied to create a strong 3-dimensional impression. So you have also shadow effects here, so that you see that this is back there. That there are several depth cues included also in this image. Integral and separable dimensions are not completely distinct. On the contrary, there is a continuum of integrality to separability. So there are many different steps in between, not just integral and separable. we can, for example, perceive the degree of redness and the degree of yellowness of a color to some degree. For example, discriminate between orange or pink. The list on next slide presents examples of display dimension pairs arranged on an integral separable continuum. A method not included there is stereoscopic depth, which seems likely to be separable from other dimensions. So here you have this overview, so it's kind of ranking. Examples of glyphs coded according to two display attributes. At the top are more integral coding pairs, at the bottom are more separable coding pairs. So this is more integral. Red, green, yellow, blue. And then it's, you see there are many degrees here, and the most separable is group location and color. So you have a group that is based on the location, so these dots or small circles are more near to each other than those. So this is one group, this is another group. But you have also color. So you can separate these two easily. So you can separate the two groups based on location. So these are the two groups. Or you can also separate two groups based on the color. These three have something in common. Therefore, they have the same color. And the other 9 have also something in common because they are black. So here it's easiest to do that because these are the separable dimensions. Here it's much more difficult to see the two options here, like here. Here, what is same color, what is same group based on location. Here you have a problem if you want to find that. So you need much more time. And then maybe you're maybe not sure. And then you have different degrees in between. You see there are different options how you can do that. The next topic is about the representation of quantity. If visual qualities increase continuously, they are called monotonic. For example, size, brightness, or height above ground. Other variables, for example, orientation, are not monotonic. It is meaningless to say that one orientation is greater or less than another, because orientation is cyclic. It's around a circle, and there is no more or less usually. So this, of course, I talk about quantity here. For representing quantity, the following attributes are effective. Size, length, area, volume, they all have to do with size. Brightness, lightness or darkness. Vividness, here it's meant higher saturation, then it's more vivid. Of color or vertical position. If such attributes are used, we can judge relative quantities at a glance, so very fast, immediately, although not very accurately. And this overview here, this ranking, this is very important. This is also about the heart of the matter of visualization. This is something everyone who wants to be an expert with visualization has to know. This is very important. It's relatively old. That's also interesting because you can see many visualizations that lack an appropriate understanding of these differences. So this publication is from 1984. so it's more than 35 years old, this information, but still many people don't know about it, unfortunately. So this is about the relative difficulty of assessing quantitative value as a function of encoding mechanisms, based on this publication from Cleveland and McGill. This figure here is from Spence. This is another book that I have uploaded for you. So you can find it there and you can read the text that is included there to describe it. So this sounds a bit difficult, but the important thing, and it's easy to understand, here, most accurate to get quantitative values. Most accurate is position. It's like position along you can measure. You can measure the difference between two positions. So this is very accurate. And this here is least accurate. If you have a difference in color density, or here is color hue, and here is color density. So these variables are not good for encode quantities. This is good, but of course this is often difficult to be applied in a map, for example. This is applied in a diagram very often. So in a diagram, this is the typical way. Therefore, we use diagrams very often if you want to compare quantities, for example. Length is also very good. And length we use very often also in maps. Angle and slope. Here you have angle and here you have slope. This is also more difficult. This plays a role, especially slope plays a role in diagrams where you have some curves, curvature. There slope plays a role, of course. Area is very often used in maps, like such circle diagrams. And volume, you also find volume in maps, but volume, as you see here, is relatively weak. It's not as good as area. Area is the better solution. But sometimes we have a problem with very large differences between quantities. Then we would have very small circles, like very tiny dots, compared to very large circles. And large circles cover a lot of the map area, which is also something we usually don't like. We try to avoid. Therefore, sometimes it's then a solution to use some volume, because then this difference is lower. And I mean, the difference in the area covered of the map is lower. And yeah, so this is very important. You have to know about this ranking here. There are often questions about this in the final exam. Length will generally be judged more accurately than area, particularly if people are required to judge the relative area of different shapes. Perceived volume is judged very poorly, as people usually using area rather than volume for their judgment. This is also important. We still often see three-dimensional diagrams also, and this is often makes it much more difficult for the readers. An advantage of area compared to length is that area is capable of conveying larger variations. It should therefore be used if relative amounts vary greatly. So I just talked about that problem between area and volume, but you also have this between length and area. But area is the best solution then, if it's somehow possible. If amounts do not vary too much, length, height, or vertical position are the best choice for representing quantity. this is also a very good example here. It shows you the problem with the differences between the numbers, differences between the quantities. This is about the USA federal agricultural subsidies for meat versus vegetables. That's not important. You just have two different quantities. Here it's meat and vegetables. With length, you have very, very small length here for vegetables. It's really hard to see that. And you have here quite large difference. And the same information is shown using length, area, and volume here. So these three versions, they show the same data, the same amounts. And here it's the important thing is not the absolute quantity, the important thing is the relative difference between the two quantities. So meat is much larger than vegetables. That's the important thing here. And the research shows that the quantities shown in the volume display on the right will be mostly judged according to the relative area of the images, not according to volume, resulting in large errors. Because here you should think about the volume. And although some depth cues are used here, you have this shadow effect here to give you the impression that this is a cylinder-shaped object. But still, mainly we deal with this area. So we handle this like it is just a flat object, just a flat two-dimensional object. And therefore, we underestimate the size of this quantity. So if you ask people how much larger is the amount of meat compared to vegetables, they will underestimate this difference here. Here they will judge it much better, and even better maybe here. But here it's so small that it's also difficult then to say how often this, just like a horizontal line, how often this fits into this length. So for this situation, this example here, area is the best solution. And this should be avoided because of this problem. And this is an example. Unfortunately, we often see such examples. I'm sure you have seen that, and I have seen it. This is really bad. You should not do it that way. This here is much better. So for the same reason, this kind of pie charts should not be rendered in 3D. This is not good, because people then, they mainly estimate these areas here. And this makes it much harder to compare. So this blue one looks larger than it really is. This green one looks smaller than it really is. So it's much more difficult to estimate the right numbers and relations between these quantities here. This one is much better. And you also have the advantage that angle plays a role here. And angle, as you know, angle is a very good variable to compare quantities. And here this is distorted, and therefore it doesn't work well with the angles. This is an additional aspect here. Mathematicians and engineers use the logarithmic plot in cases where there is a large variation in magnitude, but it is not a perceptual solution. So for perception, this is difficult to comprehend that. So we need to think about it, and it's of course not pre-attentive and takes more time. But sometimes we need it because there are so large differences between the numbers. if we need to represent absolute quantities, the so far discussed attributes do not work well. Only 3 to 5 distinct values can be reliably read using simple graphical variables such as color, size, or brightness. So what we discussed so far is mainly about the relative quantity, so to compare quantities. Now this here is the question of absolute quantities. Among the solutions to this problem are adding numbers or a numerical scale, or designing a symbol that by its shape conveys numerical values. A good example is the so-called wind barb. Here you have examples, 3 different ways that more exact numerical values can be read from a diagram. So A is simple adding numbers, and of course this has to be done carefully to avoid too much additional visual noise. Visual noise means there are too many distractors. If you have a lot of numbers in a map also, this is of course then hard to read. B, here adding a numerical scale is less exact. Of course, here you have an exact number. This is less exact because you have to interpolate between the numbers and estimate the correct value. And C, the wind barb is a kind of hybrid of perceptual features and symbolic features. So it's a very interesting also glyph here, you can say. This is an example also for a glyph, of course. The shaft of the barb represents, like an arrow, the direction of the wind. Here it's from northwest direction. So here is northwest, and this is the direction of the wind. So from northwest to southeast. The feathers, so these features here, the feathers of the barb encode wind speed. Here it's 75 knots, about 140 kilometers per hour. So this is, you will see on the next slide how this works. Someone familiar with the code can read off wind speed to an accuracy of 5 knots. So this is less than 10 kilometers per hour. But the barb feathers greatly interfere with the perception of wind direction, which makes it very difficult to identify patterns in the winds. This is a disadvantage of that method. The circle means sky completely clear. So this circle here, it also encodes distinct information. So here you have the details about the code, how information about wind speed is encoded in wind barbs. And this is calm weather. This is 5 knots. This is 10 knots, and this is 50 knots. And then you can combine this here. This is 5 and 10 means 15. This is 10 and 10 means 20. This is 5 and 10 and 10 and 10 is 35. Or here with the 50 knots, then you have 80 and so on. And if you're familiar with that code, it's a very fast, relatively fast method to get detailed numbers, relatively detailed numbers. The next topic, the searchlight of attention. The attention process is concentrated around the fovea, where vision is most detailed. So you learned about that in the vision section. To some extent, we can redirect attention to objects away from the fovea. This fovea-centered attentional field can be called the searchlight of attention. It expands and contrasts based on task, the information in the display, and the level of stress, tunnel view, in the observer. So if we are stressed, we develop a kind of tunnel view. That means we do not take into consideration things that are outside of a limited central field of view. So the outer parts of the field of view are not relevant to us if we are very stressed. So if we have to do things very quickly, we are very focused. And this focused means also that our visual field somehow it seems to be smaller. So this is called a tunnel view. If we are reading fine print, the searchlight beam is the size of the voir, so it's quite small. If you're looking at a larger pattern, it expands, so it becomes larger. And there's another term, the useful field of view. I mentioned that today because it's one of the sample questions that I've sent to you is about this useful field of view. And this defines the size of the region from which we can quickly take information. The UFOV varies greatly depending on the task and the information being displayed. For high target densities, we use a small UFOV from 1 to 5 degrees of visual angle. For low target densities, the UFOV can be as large as 15 degrees of visual angle. So that's quite a big difference. And this here you find also the answer to this sample question. So the UFOV varies with target density to maintain a constant number of targets in the attendant region. And here you have an interesting experiment, or the result is displayed here of an interesting experiment. This was part of a study by Peterson and Dugas from 1972, also quite old. The task was to detect small symbols representing aircraft in a simulation display. The green circles show the response times from the appearances of static target. Static, that means not moving targets, static, so in the same position. The crosses show response times from the appearance of moving targets. Subjects can respond in about 1 second to targets 20 degrees from the line of sight if the targets are moving. But if static targets are used, performance falls off rapidly, beyond about 5 degrees from fixation. This implies a UFOV of at least 40 degrees for the moving target task. So what we can learn here, you have on the left-hand side here, you have the response time in seconds. Here you have the angle from fixation point. So the fixation point is the center at the voir, where we have the highest acuity. And from fixation points means how far away from that point a target is located. And the green lines show response times for the appearance of static degrees. So if a static object appears near just 4, 5, maybe 6 degrees from the from our focus point, then you see we are very fast. The response time is or relatively fast. The response time is less than 1 second. So we are far away from the pre-attentive response time. So if it's pre-attentive, remember, then it's about 10 milliseconds. We hear about 1 second, much longer. But still, this is relatively fast for this kind of experiment here. But then, if an object appears about 6 degrees or more away from the fixation point, then we need much more time for a reaction. So here we need 10 seconds or more, and it's rapidly growing. You see, the time is rapidly growing. Just a bit more far away means much longer. So here, just 1 degree more is maybe 20 seconds more. It's totally different with moving objects. So our field of view is very sensitive in a quite large area. So even 16, 18 degrees away from the fixation point, we just need less than 2 seconds to react. So this is very important for a display showing objects. It's important that these objects are moving objects or blinking objects, so that there is something going on and not just static. So these are also important experiments, and it's important for us to know that. So some of these examples, I know they're a bit difficult to understand. There are many new terms. It's also clear. I want to finish here, because the next chapter about the visual variables. We will talk about them next week. But these different sections, you see, there's the searchlight of attention. There was about the quantities, representing quantity is another section, and so on. So when you learn these materials, I will send you the next part of the examination materials end of this week. If you learn with these materials, then think about these different sections. Think about the most important technical terms. What do they mean? So why is it important for us for visualization? It's important that you understand what's going on, and that you know about the most important technical terms. These are the two things. And yes, if you have any questions, again, please can send me a message on QQ. You can send me an email, just as you like. It's important that you understand these things and that you know what's going on. This will make it much easier for you to finish this course successfully, and to take more out of it for your further career and your further work. I'm sure about that. So thank you for your attention for today, and I wish you a nice day and rest of the week. Stay in good health, and hopefully we can all return to Wuhan as soon as possible. Bye-bye.